To welcome Gordon German to the stage to give his presentation on PyFEM Mesh Conversion Software Library. So Gordon has a PhD in remote sensing and artificial intelligence, and he joined the CSIRO in 1999 as a computer scientist. And during this time, he's been involved in various projects around geoscientific numerical modelling, workflow analysis, grid computing and high-performance computing. And he's currently working in the technical algorithms team, computational geoscience of the CSIRO Minerals Down Under flagship, and he joins us from Perth. So thank you very much for coming all this way to our meeting, and look forward to hearing a talk.
Thank you for that. So this morning, so far, we've heard like the big picture from Mark Gagan, and then a kind of a middle picture from Richard. This is very much a lower level, small picture, single project type thing. It's essentially a talk about a piece of software that is almost a byproduct of a larger project that we've been working on. And we started on this maybe 10 or 12 years ago, and it's kind of just at the point now where you would call it mature software, which is a nice way of saying it's getting old. But it's certainly become very usable to the point where it's almost glossed over, and many people that are using other technologies tend to forget it's there. So I'm going to briefly go over what it is, why we decided we needed something like this, the approach we took to designing the library, some of the modules that are available through it that can be called separately, and the sort of processes we went through in working in what became a very distributed team environment quite early on, actually. We were talking about 10 years ago, so it was quite new in those days, but has become more of a predominant paradigm now in design work. So the PyFEM library is an open software project, and it was primarily designed to enable the conversion of finite element meshes from one package to another. I'd started working with numerical modeling geoscientists in CSIRO, and the numerical modelers of the time would work in very discrete packages. So you'd have the mechanical deformation modelers would work in one specific package, the chemical modelers would work in a very different package, and heat and fluid would be somewhere in between. But they all were trying to actually produce a finite element or a finite difference mesh of, in many cases, the same part of the Earth's crust, which would then go into a numerical modeling package simulator to simulate the actual phenomenological domain they were working in. So the PyFEM library, which actually started as a single translator, as I said, 10 or 12 years ago, provides several benefits to people that are using these sorts of software. Generally speaking, the actual numerical solvers themselves have some basic abilities to create a mesh, but often these meshes aren't as realistic as the modelers want, whereas there are other visualization packages and specific meshing packages that can make very complex meshes, and this has come mainly out of the computational fluid dynamics field and in automotive and aeronautic design, where very, very complicated meshes can be produced. Oops, wrong button, sorry. Another usage for this is at the other end of the modeling, where once a model has been run, a simulation has been run, different types of visualization might be required, and the normal output of these sorts of solvers don't allow a lot of manipulation of the data. So, for instance, here we're converting a FLAC 3D mesh into a VTK XML format, so it can be visualized in something like Mojave or Paravision or something similar. It also became quite useful when we started getting these modelers together and trying to produce coupled solvers, where we were using solvers that worked in mechanical and fluid domains, and then solvers that were working in chemical domains, and trying to couple them together to produce a fourfold coupling of a particular part of the Earth's crust. those particular solvers, of course, used very different types of meshes, so there was a continual need to translate between the two, or convert between the two, and the PyFEM library became an integral part of that. So, as I said, PyFEM is an open source project. We wrote it in Python, the scripting language, mainly for interoperability and platform independence. Some of the sections are still written in C++, purely for computational aspects, but the majority of it is all Python, which means although it's object-orientated, it's very highly commented code, it can work across a lot of different domains. The library now, started with 1 or 2 programmers. We have contributors from all over Australia now, so we'd probably have 10 or 12 people that have written code for the library, and those people are also the reviewers for that sort of code. It's tested on Windows and Linux. There's a build every time the code is changed for both Linux and Windows installers. The code will work either in a single file mode, so it can be installed on a desktop PC, for instance, and the user may want to just convert a particular mesh or 1 or 2 meshes. It works in batch modes, so you can just throw out a whole lot of files and it will convert them on the fly. It's used that way on high-performance computing resources, so we have it installed on EPIC, which is one of the Policy Center Stage 1 large Linux cluster machines. It's installed on a large single shared memory machine, Cherax, which is one of the Cyro Altex machines. And we have it installed on the Windows cluster in Kensington, which is a large cluster running Windows HPC 2008. It can be run either by writing small scripts that will then instruct the software library as to what it is you want to do. But it was, as I said, part of a larger project, which was the Desktop Modeling Toolkit, which was a workflow tool to try and enable geoscientists who were doing numerical simulations to try and separate them from the intricacies of the actual solvers and the way they run on different platforms. And it became an integral part of that. So there is actually a GUI interface within the Desktop Modeling Toolkit for driving these sorts of conversions. Currently, the library supports, well, the first one was GoCAD, because it was originally called GoCAD to XML, because I was converting GoCAD type binary files into an XML format so that we could easily read them and then convert them to something else. But since then, we've added quite a few converter classes. SheMat is a chemical modeling package. Patran is a model builder, a mesh building package that's often associated with other packages such as Abacus. Finlay is the meshing tool that's used by eScript and run through the University of Queensland. XML for FEM is the serialized storage format for PyFEM itself. We worked with, at the time, a company called Fractal Graphics producing that format. So that will also import and export from Fraxis, their package. There's a generic ASCII converter, FastFlow, FLAC3D. These are all solvers. Gmesh and TechPlot, which are meshing programs. A couple missing from there are the standard VTK, and there's a VTK XML, and there's several others that aren't actually on the trunk that people are contributing that will migrate to the trunk over the next few months. So why we started looking at this was the fact that 10 or 12 years ago, so I'm going back a bit of time, modelers were fairly well restricted to block models. The meshes they used were block approximations to real surfaces and real-world data. And they wanted to start building 3D versions of the thing you see on the right, where you had a real-world surface describing certain faults and stratigraphic layers. There's a whole argument over whether this gives you any greater accuracy in the simulation or not, but I won't go into that. That was a necessity. People wanted it, and they also wanted to be able to see these on the outputs. So there was a need to try and build the mesh external to these solvers And that was fairly novel in 1999-2000. And we needed something that was platform independent because some of these solvers worked on DEC Alpha machines in those days. Some of them would work on PC, some of them work on silicon graphics machines. And they're all quite different. So we needed something that could be installed on all of those platforms and provide the kind of conversion that was needed to get these meshes into the solver and out again at the other side. We wanted an extensible model so that people could start adding their own converter classes. We didn't want to be the sole custodians of this and the only programmers working on it. It was just, we realized very quickly there are thousands of formats out there and we couldn't write a converter for every one of them. So we tried to make it as easy as possible for people to actually extend it themselves. Hence the open source idea and keeping it in something like Python, which was a free scripting language on almost every platform and can be installed on almost every platform available. And being interpretive rather than compiled code, you didn't need a specific environment, so people that were working for the first time on adding something to it didn't need to set up compilers, set up specific environments for it. They could just install Python. In fact, it would probably be installed anyway on most of their machines, and start coding. Even at the beginning, we had people from several different areas of expertise involved in this. There's myself, Peter Hornby, Rob Woodcock is here today, Simon Cox, and this actually became a Sigrid project for a while. It grew out at about the same time as the Sigrid stuff. Lutz Gross's team from UQ started adding classes to the code as well. And being such a disparate group of modelers and programmers, we started to realize very quickly that we needed a team approach to producing this. And Richard's touched on a bit of that, and I will in a minute as well. We ended up with what we realized was an agile model, perhaps before we realized it was an agile model of coding these things. I briefly mentioned XMML for FEM before. Certainly for testing in the early days, we needed some sort of serialization of this PyFEM conceptual model. So we wrote our own format, which was XMML for FEM, which is a extended mining markup language, was the original XMML. And that became the basis for the importers and exporters in Praxis and some of our own software as well. It being an XML representation was extensible as well, so it followed very neatly the improvements in design that came as we were building the core PyFEM module. So there's the overview of the design. Of course, we've got the core PyFEM class, and then there's a conversion class for every format that is added to the library. Such that we can convert any one particular format into another without having to write direct conversion or translator classes for format A to format B. All we have to do is convert it into a PyFEM instance and then from there write it out. Ideally, of course, you want a lossless conversion. That's never going to happen, but we do manage to, within constraints, keep all the data that is in the input files. I'll talk about that in a minute. The actual core class is the PyFEM class. It handles multiple element types. We've got a very comprehensive list of element types that it will handle. So it's got the usual 2D types, such as polygons and lines, polygons, and triangles. The 3D classes, tetrahedral, hexahedral, wedge, pyramids. You can have singular centroid classes or elements, or you can have quadrature elements, so you can have 20-node hexahedrons. We tried to add an awful lot in there in the first place, so that as other formats were added, if they had the facility for using those sorts of elements, then they could do so themselves. It can handle surfaces, subsurfaces, regions, subregions, They can be defined in nodal orders, they can be defined in element face orders, they can be defined in vector formats. You can add samples by region, by element. You can order the nodes in any particular requirement. So this core class is something that we as the core team at Kensington CSIRO put together. It's not usually touched anymore. It's pretty much a stable entity now. And the majority of work now is done in the conversion classes. And we have a template that most programmers will follow. So all conversion classes have a read file method that takes a file object. We have a read stream method so that we can drive this from some other host application. And similarly with the write methods. There are test routines in every converter, but they're not necessarily called because if the user knows in advance that all meshes, for instance, are homogeneous element types or are irregular or they're orthonormal, you can set that as a flag, and then none of the tests will be done to actually ensure that the conversion goes ahead. There's also an XML database file behind there that knows that certain formats, whenever we add a format, if there's a restriction, so for instance, SheMat must be an orthonormal element type. Therefore, an input file, an input mesh that can't be converted. If the user sets the flag saying that it is, then the conversion will go ahead. There's another module, FEMstats, which I'll go over very quickly, but essentially it's used for post-processing. So once you've done your numerical modeling, you have a whole suite of files. They're generally a time series of some description. You can go through those meshes and do time series analysis. You can do history of particles at certain points. You can create new variables. You can clip your mesh physically or in time. And just return specific portions, perhaps to be reused or remodeling a particular point, and you can then increase the resolution of that as well if you want to. There are some pre-processing functions that we added. There were certain problems with some of the GoCAD surfaces not being accepted into packages like Patran that requires a completely watertight volume, and you can do that sort of thing with this modules as a preprocessor. The FEMstats module basically runs with a set of rules. These rules are written initially by us and then on the request of modelers. However, from that point on, they can add their own rules. One rule script can have multiple rules in it, and the modelers can share these things. That's just an example of the GUI from the DMT I was talking about earlier for driving these sorts of conversions and setting some rules for a FEMstats run at the end of it. Our coding process was, as we found out, based on Agile. We bent the rules a little bit occasionally, but the essential idea was to have a 6-month goal planning. We'd work in 3-week iterations. We still do. And at the iteration planning meetings every 3 weeks is when you add issues that are going to then be either tackled or delayed for a later period. We have weekly 30-minute reviews of these to see how we're going, and of course the daily 5-minute scrums where everybody stands, the idea being that you can't stand for more than 5 minutes without getting edgy, so it helps keep the meetings short. We have the Wiki Collaborative pages for both developers and users, so there's 2 separate pages. If you're a developer, you have access to development pages where there's notes on how to build, how to write the scripts. For people that just want to use it to do a conversion of a set of files, there's a user pages. Everything's in the SVN repositories. We have a rule that the trunk has to build, so you can't go home Friday night and leave it in complete disarray. We've got about 90% coverage now on the unit tests of all the functions in PyFEM, and there's quite a few of them. And the order build is on the trunk, not on any of the branches. We started with monthly updates. It's now a little slower than that. It's probably 2 to 3 months that we put an update after somebody has added or contributed a converter class. Jira is now being used for issue tracking. We went through a number of other issue tracking softwares in the earlier years. And it's fairly typical where you assign a particular issue, it gets resolved after it becomes peer reviewed by one of the other team members. And it's not that bad. We had a bit of resistance to it at first, but everybody got reasonably used to it. And it does produce nicely commented and formatted code that's easy to debug, that's easy to add on to, even for relatively new people to Python programming, purely from the templates that are available. Finally, we do encourage people to use this software. As I said, it's used in quite a few of the numerical simulations we do, almost undercover, because typically the outputs these days are all either in VTK or in fractal graphics, Fraxis modes, and reports and visualizations in PDF are then produced using the PyFEM library. We do have a wiki, although it's membership. But if you are interested, you can just either email myself or the development team at CSIRO, and they'll add you to it so you can have a look at it. Thank you. I think I'll stop there. If there's any questions.
Questions? Do we have any questions? Okay. Yeah, great.
I was just wondering if the source code was available online.
It is available to anybody who has access to the SVN repository, but that, we can give that to anybody that's requiring access. Whether you'll get access to write back to the SVN repository is another question, but you can certainly have access to the code, yes. Sorry? It's under a GPL.
Other questions? I just have one quick question. The topic of the session is data everywhere. What are we doing with all of these pesky data generating programs? How are we managing all the data that's coming in and going out?
It's not something that PyFEM itself does, but it's certainly something that we have to be aware of, particularly if you're working on one of the HPC resources where your data will be regularly dumped after 2 weeks if you haven't moved it off the data directory where it's been produced. Typically what we've done is archive the data for the users. If a particular user has a project of, say, 6 months lifespan, we archive it for them in a given area. It used to be on the petabyte storage facility at IVEC. I think we still use the new one for that. However, the size of these meshes gets rapidly very, very large. We're doing, currently we're worming an area in the Pilbara at 50 million pixel resolution data sets, and there's about 100 of them. And then when you start doing the mesh conversions for that, you'll have 2 or 3 terabytes of data at a time, so it is a problem.
Yeah.
So PyFEM have to load the entire data set into memory for the conversion. So they have to load the entire data set into memory for the conversions, or can it screen it?
To do the inversion or the conversions, it will do it. By default, it will do one mesh entirely in memory, but there is a compartmentalization scheme that can break it up if you're using MPI.
Anyway, we can have that discussion.
Yeah.
I suggest you catch up over coffee. I think that might be a good discussion. So thanks very much, Gordon.
Thank you.
Presentation.